happy to have M.Inaba, and he will be continuing the course from the morning.
Thank you very much. Is okay? Okay. First, thank you very much. First, I'd like to thank the organizers for inviting me to this nice conference and giving me a chance to talk here. The title of my first lecture is moduli space. Regular singular parabolic connections. And isomonodromic deformations. And content of this talk is joint work with Iwasaki and Professor Saito. So first, today I will talk about moduli space of regular singular connections and isomorphic deformation. And in lecture 2, I will talk about irregular singular connections and generalized isomorphic deformations. And before I announce in abstract about unfolded generalized isomorphic deformation, but so I'm sorry, I cannot complete the proof of unfolding. So in lecture 2, I only talk about moduli space, which expect to have unfolding of generalized isomorphic deformation. So, anyway, today is a regular singular connection. And first, I give a definition of parabolic connection and its moduli space. This is definition and moduli space is given in the talk by Professor Saito, but I repeat it again. So first, I fix a smooth projective curve. Of genus G of a complex number field. And take distinct endpoint in C. And write dt to be the effective divisor on C, like dt. And we take a tuple of complex numbers. Which is a data of exponents satisfying a certain residue condition, which is sometimes called Hooke's relation. So summation of nu ij is integer. Under this data, I recall the definition of parabolic connection. E nabla Lij this is called P new parabolic connection. If this E is an algebraic vector bundle of rank R, and degree is A. Nabla is algebraic connection admitting force along dt, that divisor dt. This is an algebraic connection. And thirdly, Lij is a filtration on the fiber of the vector bundle of the point Ti. No, I'm sorry. This is 0. This is okay. And satisfying this filtration satisfies this condition with respect to the residue of the connection. This condition means that residue of nabla, this is an endomorphism of the fiber of the vector bundle, and so endomorphism of this vector space. And this condition means that for certain basis of this vector space, this linear map has a representation matrix like this type. So residue endomorphism has the eigenvalues nu I1 nu IR. This is the definition of parabolic connection. And I will definition of stability, which is already explained by Professor Saito. Take a tuple of rational numbers, Q and R, satisfying R, and assume alpha j are all distinct. Then we can define the stability of parabolic connection. Sorry. Parabolic connection lambda Lij. This is alpha stable if it satisfies for any subbundle of E satisfying for any subbundle preserved by the connection lambda. This inequality holds. No, rank. Sorry. Degree F. Ij alpha Ij. Divided by rank R, rank of F. This is less than degree E plus alpha Ij dimension Lij of Lij plus 1. So if F is not the condition that F is preserved by lambda, this condition we don't consider this condition. This stability inequality is the definition of stability for usual parabolic connection, usual parabolic bundle. And we extended the definition of stability for parabolic connection. So I consider this type of stability condition for the construction of moduli space by GIT construction. So if a parabolic connection satisfies this stability, then corresponding parameter space is a point in the parameter space becomes stable with respect to some reactive group. So then we can take quotient and get moduli space by GIT construction. So yeah. Is it okay? But we construct some certain parameter space and divide by some reductive group. So we only embed certain space, but I don't know exactly the closure of this embedding. So, essentially it comes from GIT. Yeah. That is a certain relative condition. So, rational differential form on this rational differential form should satisfy total. No. Should satisfy this residue condition, and so by using this, we should have the degree of the determinant bundle of E should have should be Uij. Should satisfy this condition, and I put this integer a. So yes, this should be an integer. Yes, degree of the bundle, minus of degree of the bundle, determinant bundle. And then we can define the moduli space of alpha stable parabolic connection. Moduli space. Full flag. Huh? Yes, full flag. We can also consider generalized flag, not necessarily complete flag, and in that case we can obtain parabolic connection of a certain spectral type, we call spectral type, and we can get similar moduli space. Yeah. But today I simply consider a full flag type. Moduli space of parabolic. There exists a moduli space of parabolic connections. And which is smooth and quasi-projective. Of dimension to R square G minus 1 plus 2 plus in R minus 1. And as in the question, the previous question, we construct this moduli space of alpha stable, moduli space of alpha stable parabolic connection by a certain GIT construction, and for the construction of the moduli space, we should consider as stability. Moreover, there exists an algebraic symplectic form on the moduli space of our connections. And as in the talk by Professor Saito, we can describe the tangent space of the moduli space by first hypercohomology of certain complex. And we can describe this symplectic form by certain pairing on the hypercohomology, which is like something like trace pairing. And, so next, I explain about isomonodromic deformation. Me? G. Sorry. G is this G. G is the genus of the curve. Sorry. Sorry. Genus is, we can take, this is any genus. Dimension is given by this number, but we should assume that the modular space is non-empty. If the modular space is non-empty, we have its dimension of this number. So next, I will go to the isomonodromic deformation. Isomonodromic deformation. So let us consider the moduli stack of smooth any-pointed curves. Moduli stack. And taking certain covering, some smooth white R covering, there is a universal family of any-pointed curves. And over this parameter space, we can consider a relative moduli space of parabolic connections. Can consider moduli space of sorry. We can consider relative moduli space of parabolic connections. Parabolic connections. And I want to consider this space T as a space of time variables for the isomodromic deformation or isomodromy equation. So I will construct isomodromic deformation or isomodromy equation on this family of moduli spaces. For constructing the isomodromic deformation, it is necessary to consider the Riemann-Hilbert correspondence. So I briefly prepare the modular space of representations of the fundamental group. So for simplicity, I take a universal cover of this space T. Then bring back the family of curves to this universal cover. The family of curves becomes topologically trivial. So we consider the representation of the fundamental groups. Fundamental group. So this is the space of homomorphism of the fundamental group to GLRC, and divided by the adjoint action by GLRC. But for the definition of the quotient, we consider invariant ring of this affine space with respect to the adjoint action. So we should take a categorical quotient. So I write by two-line quotient. Adjoint quotient. And in this modular space of fundamental representation of the fundamental group, we can consider a locus where the representation of the fundamental group satisfies a condition that if we take a loop around singular point Ti, then the local monodromy of this representation around the point Ti has the eigenpolynomial equals to T minus exponential of 2 pi root minus 1 lambda, nu ij, where j equal 1 to r. Yeah, and we consider this locus. We can consider the family of modular space of the representations of the fundamental group over T tilde. Excuse me? Excuse me? Yes, yes. So, yeah, this is a good comment. Because family of universal family of curves of this T tilde is topologically trivial. So I don't I didn't write yet, but the family of the moduli space becomes locally becomes trivial family. Consider the family of moduli space of the representation of the fundamental groups. This is relative moduli space. Representation. And so we have a family of moduli space of connections, and also a family of moduli space of the fundamental groups. And between the moduli space of connections and the moduli space of the representation of the fundamental group, there is a Riemann-Hilbert morphism. It is characterized by like this. If we take a parabolic connection, then it induced a holomorphic connection restricted to C tilde S minus T tilde S. This becomes a local system and corresponds to a representation of the fundamental group. So this determines a point in this moduli space. So we define RH, Riemann-Hilbert image by this representation. So we can define morphism, Riemann-Hilbert morphism by this formula. And this is, of course, commutative. This Riemann-Hilbert morphism is almost isomorphic, but there is some exceptional divisor, exceptional locus. So this is a bimeromorphic morphism. And this is a Riemann-Hilbert morphism. This Riemann-Hilbert morphism is a highly transcendental morphism and never algebraic morphism. And as in the previous question, previous comments, this family is a trivial fibration because T tilde is the universal cover. Pi 1 of T tilde is trivial, so this is trivial fibration. So there is a foliation. This triviality? No. bimorphic. So if nu is exponent nu is generic in the sense by Professor Saito's talk. If generic, then fundamental theory of Riemann-Hilbert correspondence says that connection with the regular singularity corresponds one-to-one to representation of the fundamental group or local system on this space. So if nu is generic, this is analytic isomorphism. But if nu is special, for example, certain types like this eigenvalue, some eigenvalues are the same. Then we can choose like scalar matrix. Then we can choose many parabolic structure. Parabolic structure is parameterized by flag. So the fiber becomes parameterization of this flag. Ambiguity of the parabolic structure becomes flag. Yeah. For the for this, this is the analytic resolution of singularity, but there is algebraic resolution of singularity of this modular space of the fundamental group, and that is given by Yamakawa. Yamakawa constructed the modular space of filtered local systems, and that gives a resolution of singularity of this modular space. And he gives analytic isomorphism between the modular space of parabolic connections and modular space of filtered local system. I understand.
How does the Riemann
parabolic weights? Parabolic weights. So this morphism is defined by a fixed alpha. So if we change alpha, modular spaces are birationally equivalent, but not necessarily isomorphic. But so yeah. In fact, this morphism is a proper bimeromorphic morphism. A holomorphic map. Holomorphic morphism. So 5/3, this gives analytic resolution of singularity of the family of modular space. And the properness of this morphism is difficult to prove, but we can do it. And as I said, there is a trivial foliation on the family of moduli space of representation of the fundamental group. Comes from trivial fibration. And pre-impact by the Riemann-Hilbert morphism, we can get foliation on the modular space of parabolic connections, which is called the isomodromic deformation, or isomodromic foliation. Isomodromic deformation. This is a definition of the isomodromic deformation. I will say about the geometric Painleve property of the isomodromic deformation. Geometric Painleve property. So statement is easy to write, but before writing the definition of the geometric Painleve property, I will prepare a picture. There is a family of modular space of connections, and here is just, and we consider the space T as the space of time variables, and there is a family of modular space of connections, and take any path gamma in that space of time variables. So we consider path in this space of time variables, and for any point in the modular space of connections over the initial time gamma 0. So x corresponds to some parabolic connection. Then there is a unique lift gamma tilde, lift of gamma, lying over a leaf, lying over a leaf, an isomodromic leaf of the isomodromic foliation, isomodromic foliation. This is a definition of geometric Painleve property, and if I explain in this picture, gamma tilde is a lift of the path gamma, and for simplicity, I assume that gamma is a closed path. So So this comes back to the initial type gamma 0. Then lift gamma tilde. This is lift of gamma, which is an analytic continuation. Along isomonodromic deformation, isomonodromic. Deformation. So this is a solution of the isomonodromy equation, and consider the analytic continuation and coming back to the initial time value. And the geometric boundary property means that there is always a limit point coming back to the initial time value. So if we consider solution of the isomonodromy deformation and starting at some time, initial time, and coming back to the initial time, then we don't know the solution of the isomonodromy equation is convergent or divergent. But this geometric boundary property means that there is always a solution of the isomonodromy equation is always convergent. And this geometric boundary property follows from the properness of the Riemann-Hilbert morphism. Property of the property of this Riemann-Hilbert. Property of Riemann-Hilbert. Sorry. Properness of the Riemann-Hilbert morphism. So fiber is always compact, and we can take a limit. Some statement. Sorry. Sorry, theorem is that this isomonodromic deformation satisfies the geometric boundary property. That is the theorem. For any foliation with which is horizontal to the initial time value, time space, we can consider the concept of geometric boundary properties. But the special isomorphic foliation satisfies this property. That is the theorem. Sorry. Yes. For the definition of the foliation, exactly, we cannot define this foliation over the exceptional locus of the restoration of singularities. So we can give a precise definition of the isomorphic deformation, and I will give you in the next section of the precise definition of this foliation. And exactly, as a general theory of foliation, foliation corresponds to a certain subbundle of the tangent bundle satisfying certain integrability condition. And I will construct that subbundle. And it is constructed algebraically. Construction of Isomonodromy equation. So there was a family of modular spaces of connection, and we write it pi. Then there is a differential tangent map between the modular space. Differentiating pi, we can get pi star t. This pi is a smooth morphism. This tangent map is a surjection of the vector tangent bundles. And we want to construct splitting. Splitting of this surjection such that the image is a subbundle of the tangent bundle satisfying integrability condition and giving the isomorphic foliation. For its construction, we take a vector field over the space of time variables. So we take vector fields over a Zariski open subset of T. Zariski open subset T prime of T. Then there is a family of n-pointed curves over T. And this tangent vector field corresponds to a certain morphism from T prime cross spec Ct over T square to this space T. This tangent vector field corresponds to this morphism, such that a restriction to T prime is the given inclusion. And take the fiber product, and we write CV and TV. And we write this space T prime V, whose structure morphism over T is given by V. Over the restriction of the modular space, there is a universal family. Over M equal M alpha nu cross T prime. Universal family of parabolic connections over the restriction of the modular space. And for the construction of the isomorphic deformation, we want to extend this connection to a logarithmic connection, direction of the logarithmic connection with respect to t bar direction. And sorry, I write M prime and I write M prime V as M cross spec CT over T square. This is over T prime cross spec CT square over T prime. And we define a concept of horizontal lift of this relative connection. EV, nabla V, LV, IJ. This is a horizontal lift of the relative connection E tilde, nabla tilde, L tilde. If EV, this is a vector bundle on CV cross M, CV cross T prime over T prime M prime V. This fiber product is taken with respect to this twisted morphism. And of rank R. And nabla V. This is like something like connection, logarithmic connection. Omega 1 CV over T prime log dTV. Precisely, we pull back this logarithmic differential to M prime V and tensor with EV. And this is a connection. So I write the right. Nabla V is an integrable connection. Integrable connection. So omega 1 log D, this is locally generated by something like dz over z and dt. Locally generated by, sorry, this is locally generated by dc over z and dt. And in this reduced scheme, we have dt. T square is 0, so t dt is 0. And there is more condition, and such that LV is a filtration. TV. This is TVI. This is a filtration. LV. I1. Filtration such that it is preserved by the connection. So omega 1 CV CV over T prime log dTV. And for the composition of logarithmic connection with CV over T prime V. This is T V. Composition. There is a canonical morphism from this logarithmic differential to the relative differential sheaf, and the composition becomes a relative connection, and it should satisfy V minus Uij. This sends LVIJ to LVIJ plus 1 for any of J. And EV nabla bar V LVIJ. This is a family of parabolic connection over M prime V, but tensoring OM prime V over T. This is isomorphic to a given connection, family of connection. This is a definition of horizontal lift. Because isomodromic deformation means that the corresponding monodromy data corresponding to the connection should be locally constant. So connection should be extended to a flat connection. So we require the existence of horizontal lift, and we can always construct proof that there always exists a unique horizontal lift. Okay. And then the corresponding relative moduli, relative connection family of relative connection. This is a family of parabolic connection. Family of M prime V. Then this determines a morphism from M prime V to the moduli space M alpha nu. And M dV. And this corresponds to tangent vector field. Tangent vector field in the modular space of parabolic connections. Then we can define splitting of the tangent map. We can define prime to T to tangent band, which is splitting of the tangent map and satisfy the integrability condition. And this determines the foliation. The foliation F alpha nu. So by construction, this is splitting is algebraic homomorphism. So we can say that the isomonodromy equation is given algebraically. This is my talk. Thank you. Thank you. I stop here.
Yeah, do people have any questions?
Why this horizontal section correspond to algebraic contraction of the isomonodromic equation?
Mm-hmm.
I cannot understand why this correspond to considering the such kind of D,
mm-hmm.
is I don't know why this D correspond to the isomonodromic equation.
So if we construct isomorphic deformation, restricted to the isomorphic foliation, we should have the corresponding monodromy representation should be constant. So this should satisfy a local system, both for z direction and for t direction. So we should extend the fiber connection to flat connection to total space. And And restriction to the isomorphic foliation, we have locally flat connection, and modulo t taking t square, modulo t square, we should get horizontal lift, and so yeah.
Any other questions? Okay, if not, we'll thank the speaker again.